Welcome to Module 24 on data augmentation for robustness. By the end of today, at the end of this module, you should be able to explain what data augmentation is and why it can improve robustness and generalization, distinguish between good and bad augmentation strategies for a given task and modality, implement simple augmentation pipelines in Python for simple tabular and two-dimensional image-like data, analyze the effect of augmentation on training and validation/test performance, and diagnose when augmentation is acting like helpful inductive bias versus when it is hurting. So imagine we have the situation where we have a small data set, a flexible, in other words, a high capacity model, like a radial basis function with an SVM or some large neural network. And imagine we obtain good training accuracy but mediocre test accuracy. So far we have a lot of tools in our tool belt that allow us to respond to this kind of challenge. We might regularize more, so we do L2, maybe we'll do dropout a bit later. We'll collect more data. This can be expensive and maybe not even possible in some situations, but it is a reasonable thing to try to do in some situations. And we could potentially change the model, so try to make the model more simple, try to make it more constrained, choose an entirely different architecture, and so on. So data augmentation is yet another lever. It could be the fourth or maybe fifth at this point. I think I've skipped a couple of different responses. The goal of data augmentation is to synthetically expand the training data with label-preserving transformations. Take the training data itself, perform some transformations, preserve the labels to the maximum extent possible, but then generate new data, like synthetic fake data, essentially. The intuition is if we know the label, if we know that the label should be invariant to some changes, the label shouldn't change given some small changes to the inputs, like small rotations, a little bit of noise added, then forcing the model to be consistent with these new, somewhat slightly different models should help it generalize a little bit, right? So if you synthesize data that looks like the old data, but it's different, the model should attend to both of them when you're training. It should be able to deal with small perturbations in new samples we obtain in validation and testing. So what counts as label preserving transformations, and when does augmentation help, and when does it actually potentially break the problem? So let's again scaffold our concepts. Data augmentation is defined as any deliberate transformation of training examples to create new synthetic examples that share the same label space or appropriate labels and are used during training. So this can mean for an input label pair, XY, in transformation T, we create a new label pair, a new pair, a transformation on X and Y prime. Hopefully, usually, Y prime is the same thing as Y, so we're not changing the labels, ideally. The set of allowed transformations will be drawn from some distribution, T, where T is approximately this probabilistic distribution over T. A label preserving transformation is, we call that T, is one where for the task, humans or some magic oracle that knows the perfect label for a data point would agree that the true label does not change. This is maybe a bit subtle, but I'll give you some examples. In image classification, a small rotation, like if you take a photograph and then just rotate it by 5 degrees, the label for what's in that image shouldn't change. If you have a photograph of a dog, rotate that image by 5 degrees, the image still contains a dog. If you take that image of a dog and then crop it in such a way that you zoom in to just the dog, then the label shouldn't change. If you just increase the brightness a little bit, increase the contrast a little bit, it's still a dog. In text, you might have just a bunch of text and you're trying to predict something like sentiment. So you have social media posts for some reason, you're interested in that area, and you want to know, does this person feel positively or strongly towards a product, a movie, a TV show, a political candidate, what have you. And changing small, what words for others, in such a way that the sentiment should be maintained, that's label preserving. So a sentence like this movie has a good plot, to changing that to this movie has a good story, or this film has a good plot. Those smallest changes don't change the overall meaning, so the overall label should be preserved. Some changes would change the meaning, right? So this movie has a bad plot, or this movie does not have a good plot. Like those changes ought to change the labels. So when we're changing the data, this is again very abstract. We want to make those changes in such a way that the labels are not going to be suddenly changed, and we're not really sure what to do with the result. So augmentation basically encodes this belief like we have data point X and we have a transformation on X. If they're related in a certain way and they're close, the model's predictions should be similar for both X and the transformation of X. This won't always be true, and I'm going to leave it to you as a little exercise for yourself to ask yourself, like, when is it not true? We'll talk about some related answers to this question in this module, but think about transformations and think about how getting the transformation wrong can make augmentation go bad. So there's different kinds of augmentation, and those augmentations can occur across different axes. There are like rotations, like I mentioned. There are flips, so you swap around the horizontal axis or the vertical axis as crops, like I mentioned. This word should be color. COLOR is not English, so I'm going to try to fix that spelling to make it correct in a moment. Noise, adding a little bit of noise, blurring things, cutting things out. This is all like changes to images. Text can be changing one word for its synonym. Maybe you take English text, translate it to French, and then back into English. The result should have the same meaning, but the words might be a little bit different because of the translation process of English to French to English, but the label shouldn't change. You might randomly delete some words that might not be important, and you might mask some words, which means basically taking a word and replacing it with like a special token that says like word or something like that. Like not just the word, but like a token representing like a mask that hides the actual token word behind it. In audio, you can stretch the time, you can add or remove white noise or silence. You can change the pitch a little bit, although hopefully uniformly, because some humans' pitch can have an effect on like downstream processing. If you're trying to figure out how someone feels about something, the tone of voice can carry a lot of information. One thing I used to do a lot of is like if I had say I had a 16 kilohertz audio sample, I take all the even samples and all the odd samples, separate those into two separate audio streams, interpolate between all the evens and interpolate between all the odds. So I still ended up getting 16 kilohertz audio, and suddenly you've converted one series into two that are extremely similar but somewhat different to each other. Believe it or not, that kind of augmentation can work in a lot of situations like the ones we're going to explore today. In tabular or 2D data, where you have like data points and you have measurements as columns, adding a little bit of noise, like jiggling the numbers a little bit, doing bootstrapping like we talked about. Mix-up is a topic for a future module, but there's different kinds of ways you can modify the data. So it depends on the modality. So one axis is the modality, and we'll have different changes based on what modality you're dealing with. Another axis might be invariance versus equivariance. Invariance means no change. Predictions shouldn't change. So like a small translation of a digit, like moving a written digit, a handwritten digit over by a few pixels, shouldn't change the nature of what digit it is. Adding a little bit of noise on a measurement shouldn't change the prediction. Equivariance is different, right? So in equivariance, prediction should transform in a predictable way along with the changes to the data point. So imagine, you want to, you're doing some map application and you have an image of an arrow and you want to do a rotation of that image to determine whether you should go east or north or west. Obviously, if you're rotating the map in such a way or rotating the arrow in this map space, then the predicted direction might also rotate, right? So you're going to have to, in some situations, be wary of the difference between invariance and equivariance, and make sure your labels are potentially changing, as long as they're changing in ways that you're confident in the correctness. So here's augmentation in the pipeline. I'm just going to turn off a couple of these first. So you can again download the slides and play around with this. This is the original training data. We have, this is the two moons yet again. One moon is blue squares, the other moon is red triangles. And this is the original training data. And imagine for some reason we determine that this isn't enough. We're getting poor generalization performance. We want to add more data to have better models. So only during training, I can take these data points and I can just move them around a little bit. So I've augmented, things that the scales have shifted a bit between the first and second iterations here. But each of these kind of light colored squares and triangles basically just represent, shifted versions of the original data. So I just moved the data and jiggled it a little bit. Those new jiggles become my augmentation data. And I only apply this to the training data. So now I can take all of my blues, both the original in dark and the augmented here in lighter color, for both classes, and train a new model to differentiate between these two groups. I might use like an SVM like I did in the previous theory module. And the notion here is that we ought to get better performance, especially during generalization. Just a little point here. This is a little bit irrelevant, but not so much. This gray area here is just the test data. So for this particular example, these are all different data points. You can see, the test data more or less agrees with the data generating process distribution. The test triangles are close to the train triangles. The test squares are close to the train squares. This is kind of what we assume to be the case between training and testing. I'm mentioning it here just because the data we've augmented ought to be similar in meaningful ways to the test data. So we're not just augmenting this completely random data. Like this augmented data is still going to be within our distributions. It's still going to match our expectations. But I also got to mention that we're never going to augment the test data. I should have said never with quotes, because at the very end of today's module, I'm going to mention briefly situations where you might want to augment the test data. But in almost all of the practical cases, augmentations are applied to training, not to testing. And a quick note for why that's the case. If you have a lot of test data and half of it is fake synthesized augmented data, and you're computing how well you're doing on this augmented data, well, what that tells you is how well you classify fake data, but it doesn't tell you how well you classify real data, right? So at the very least, your performance metrics will be way off. A little anti-example on augmentations that just don't make sense. So just because you can do augmentations doesn't mean you should. This actually comes up occasionally. I teach a course on AI in medicine, and often students have not necessarily retinopathy, but they have other kind of medical imaging data sets in which some transformations don't make any sense. So we have these fundus images. This is the original image. This is actually from Wikipedia. I should include a link over here. But this is not my image. Our task is to look at these images and classify them as no diabetic retinopathy, mild diabetic retinopathy, or moderate diabetic retinopathy, and so on. You might have other classes as well. So you're trying to classify that image into one of these categories. We're going to use some standard image augmentations. We're going to do rotations, flips, crops, brightness changes, contrast changes, and so on. So what can go wrong? Well, take horizontal flips. So some retinal features are left-right specific. So here we have this sort of slight. I'm not a medical expert in this domain, but here, flipping can produce anatomically impossible images. So imagine you have a CT scan of the chest, for example. The heart should be on one side of the body, essentially, or the stomach on a particular side of the body. If you rotate, or flip the image around the spine of a person, it's not going to make any sense for most cases. I understand sometimes the heart, the organs can move inside, but anyway, you understand what I'm saying. Some left-right configurations are medically plausible, and other left-right data are not medically plausible. So flipping in this way wouldn't make any sense. You could do some aggressive color shifts. Here, color is written correctly. So small changes might be okay. There might be small differences in cameras. This is actually a good thing, right? So you don't want to overfit to the the focal length and the other camera characteristics of a particular sensor. So adding some modifications, adding some noise might be a good way to mimic different kinds of cameras, different kinds of sensors that you might have in practice. But very large shifts might either erase or hallucinate subtle regions. Here, as I understand, this darkened little patch over here is the region of interest clinically, but if we kind of redshift everything as if we're, going very slow compared to the speed of light, it's just whatever, it's a joke. If we redshift the image so that this kind of patch disappears, then we've lost the crucial information that tells us about the label. And then if we crop in this kind of thoughtless ways, this can also be problematic. Here's the original data. Here's a central crop where this might be okay in this case because we've captured a lot of the clinically relevant information. But if we crop in such a way where, again, we've cut out the clinically relevant information, this visible patch here looks perfectly healthy. And then we might, say, well, originally this is a pathological label. This is my crop. I'm assuming I can keep the same label, but this image doesn't show anything pathological, so it would be, the label would not be correct. So this violates the assumption that the label is invariant under the chosen transformations. In each of these cases, the label might be either irrelevant or it would vary based on these transformations. And the idea that the underlying samples are drawn from the same underlying data generating process is also false. Like the data generating process won't generate images that are this close in or flipped in this implausible way, or maybe no camera will be redshifted to this extent, so it's implausible. The result is that we have all of these augmented data points now that we're going to train a model on, but the model is going to be inconsistent. It's going to make predictions on weird data that don't make any sense, and performance should drop drastically, at least in generalization, but maybe even in training. So be careful, with what you're doing, as usual. So one reason we might want to use augmentation is that the real-world problems are imbalanced. So fraud versus non-fraud. I'm not in finance, but I can imagine that 99% of transactions are not fraud, and the 1% that we're looking to find are fraud are drastically outnumbered. You might have rare diseases, again, where 99% of the population don't have that disease, and only 1% or fewer do. And often you have situations where the positive and negative class have skews like 1 to 50 or 1 to 100 or something like this imbalanced. Even if it's imbalanced like 1 to 5 or 1 to 10, that can often be enough of an imbalance that a model that you're just saying the only kind of criterion you're giving to it is minimize the error, then a model might find that, well, I can get 99% error, 99% accuracy, say, in this situation. If I'm always guessing the majority class, then, and you're reporting your accuracy, and look, I'm getting 99%, isn't this great? I've seen PhD students at other universities fall into this trap. This doesn't work, right? So you have to use the confusion matrix to see if all of your predictions are of one class or if an overwhelming majority of them are in one class. This is majority class classification, which is an undesirable state to be in. Maybe the decision boundary is as purely shaped or is totally irrelevant to any data you might have. So it's bad. So if you want to, you have this total difference in the number of instances of each class. A simple naive fix would be, well, take the minority class, take the class with fewer examples and just copy the examples and then copy and paste them, right? Literally just copy and paste the minority class. This could actually help a little bit sometimes because at least the model won't fall into the trap of just recognizing the prior distribution of the classes with regards to each other. But obviously, you're going to have multiple points with the exact same values. So the many models will just overfit to these exact points. You're not actually learning any variation. You're just looking at the small amount of data you actually have and just seeing many, many copies of that exact same thing. So you're not really thinking about generalizability or variation, which is too naive. In comes SMOTE. So SMOTE is this paper from 2002. It stands for Synthetic Minority Oversampling Technique. So they took the TE there. The idea is for each minority example or some random subset. So you don't have to take all of the minority data points. You can only take some random subset of them. For every one of those examples, find k of the nearest neighbors to it. K can be usually about 3 or 4 or 5. And then we will generate synthetic points by interpolating between them in feature space. This is the mathematical way we'd express this, but maybe can I zoom in here? Maybe if I, be good. Okay, so this is all my data. So here's my, I'll just remove this also. Yeah, so here, these gray circles are the majority class. I have a good amount more of them than I have of my minority class. Here I technically have five minority neighbors here. I want to augment this data set with like synthetic examples that are still somewhat similar to the examples I already have, but not exact copies of them. So as you can see, here I randomly chose, well, pseudo-randomly chose this central data point. I've highlighted it in orange, but this is still a member of the minority class. And I found like its 2 nearest neighbors. I've drawn lines between them here in blue dashed lines. So this red triangle up here and this red triangle down here are the k equals 2 nearest neighbors. If you interpolate between them, if you find a point along this line somewhere, you could just imagine a data point existed there, synthesize a data point at that exact point, and then that becomes a member of your augmented data set. And indeed, if you click on here, you'll see I've interpolated a bunch of them. So like on this line, I've made like 3 interpolations on each of these lines. You can interpolate with just 1 data point along this line, or 2 or 3 or 4. This is a hyperparameter. Okay, so hopefully this idea is getting across. All SMOTE does is it will choose either all of your data points, but usually a small subset. It'll find the nearest neighbors to each of the data points you've chosen, draw a line between them, and then just synthesize new data points along that line. These new data points are similar in many ways to the other data in the minority class. So this fills in the minority region with points that are plausible. So like these points all look like they kind of seem anyway naively to be plausible. This ought to reduce overfitting and naive duplication. This I should have the umlaut on top of it. I might fix that too. This works as feature space data augmentation for classification. So you would do this and then you would learn your models to do classification. Of course, as always, nothing is perfect. There's no silver bullet. These caveats assume the minority region is reasonably connected in feature space, and you can create synthetic points along class boundaries if class boundaries overlap. Sorry. So this does assume that minority region is reasonably connected in feature space. So here, like these 2 categories are quite far from each other, but if these 2 regions were close to each other, like there's no guarantee that this area here that I've kind of highlighted in blue with this line, like it's possible that if these 2 classes are very close to each other, that actually this region should be the gray circle region, and we should be carving out something much more detailed, and it's not just like a big, homogeneous ball around these points in which every data point is a minority class. Maybe there's all these pockets that I'm ignoring through this assumption. Yeah, and the second one is that SMOTE can create synthetic points across class boundaries if classes overlap badly. So imagine if, again, these 2 regions are close to each other, and I have a point where I'm indicating over here that I want to synthesize data points from. I have another point somewhere here amongst the gray circles. I draw a line between them. All the synthesized points over here, a lot of them would end up being synthesized in the region that is mostly dominated by gray circles, and then therefore might be better candidates for the gray circle class than the reddish triangle class. A little bit of math. Augmentation can be thought of as a modified empirical risk. So without augmentation, training minimizes the empirical risk. We've seen this many times already. This is without any kind of regularization. With augmentation, we can imagine drawing transformations t from this probability distribution and training on a modified set, the transformations of x and the original labels y. So for the augmented part, so all of our augmented data points, the empirical risk function looks very similar. I'm assuming that the numbers of samples are the same here, so I'm still taking an average. Here, I'm kind of taking an average over expectations. I'm going to skip over this for now. This is not going to be crucial for you to know, but there's some reading about that kind of goes into some more detail about why this is the case. I'm not taking the average over losses. I'm taking the average over the expectations of losses given a family of transformations I could potentially have. Okay, I guess that's an explanation. Like, there's lots of transformations I could have, and I want to kind of guess over all of those transformations what would my empirical loss look like. This is actually somewhat similar to our conversation about latent spaces. The transformations themselves can be kind of a latent variable. Like, I have lots of possible transformations. All of these possible transformations will result in different losses. So I take the expectation over all of these transformations, and I think the losses of each of those possible transformations, and get the average over the expected transformations over all of the data points I've produced, gives me a augmented training empirical risk. So here we're not just matching labels on the original points x sub I like we were in the original empirical risk. We're asking a model to perform well on like the entire orbits or regions of transformed inputs, which we've called T of x sub I. So don't just perform well on the original data, but also perform well on these possible transformations. And this encodes like approximate invariances that we have to believe are valid. We've talked about that a moment ago. If the set of transformations matches real-world like variability, like real-world like noise that we talked about in the bias variance trade-off slides, this is a better surrogate for real deployment risk than the original empirical risk, because it kind of encodes the idea of inherent flexibility or variance in observations, if that makes sense. So before we were in this first loss function, we were in some point of view too fixed on the specific training data points we have, and then we were assuming something about generalizability, whereas here this expectation sort of builds in the notion of variability, expected variability in the loss, or the empirical risk, I should say. Even though that has the nice quality of being a good representation for real-world variability, you can't use the augmented empirical risk alone. You still want to combine these two risks together, because the first one is real data that you actually have observed, and the second one is still fake synthetic data that we can never be too certain about. And here are some recent-ish papers that you can dig into that talk about kernel theories of modern data augmentation and so on. So let's talk about noise injection as implicit regularization. So imagine we have this our familiar linear model with a squared loss. So here, like, there's no bias term, but this is the familiar linear model with parameters w and inputs x, and we have the familiar loss function, right? So for every sample, this is a familiar squared differences loss. Now, our augmentation is not going to be something like SMOTE. We're just going to take a data point x, and we're going to add some noise epsilon to it, producing a new data point x prime. Epsilon is drawn from the normal distribution with zero mean and sigma squared variance, and that's it. This is going to be a diagonal matrix. It doesn't have to be, but here this is a diagonal matrix. So like it's zero off of the diagonal. So now you've added a bit of noise to your original data, and now you're going to train on just x prime and y. So the labels don't change when you just add some jiggle to the so we can multiply the weights w sub t across these this internal parenthetical x plus epsilon, giving this a slight expansion, and then everything is still squared. When we apply this square to each of these terms, we get this longer set of three terms. This is the cross term, where we're kind of multiplying the thing with itself. So this cross term is going to, so I mean, it's left as an exercise if you want to go from this expectation to this line over here. This cross term will go to zero because the expected value of epsilon, as we've defined it, is zero. The average of the noise we're adding is zero. So the expected value here of this little factor will go to zero. This entire central term will then therefore go to zero also. And so also the expected value of the weight times the noise squared. This is just the sigma squared, which we get from here, from the definition of the noise, times the 2 norm of the weight vector, again by definition. So we can rewrite that last term as well. And then we can just rewrite this expansion as, the expected value of this big square difference between the labels, the predictions and the noisy perturbations, is the original loss of y minus the predictions of the clean data, plus sigma squared times the 2 norm of the weights. And you might recognize this. This is almost exactly the L2 penalty, right, where we have the 2 norm of the weights back from the L1, L2 regularization module. So in other words, training with small Gaussian noise added to inputs is roughly equivalent to the original squared loss plus an L2 penalty of the weights. In this case, weighted not by lambda, but by sigma squared. So the reason why I think this slide is very interesting is that this is a concrete, although theoretical, example of augmentation in the form of just perturbations to the data that essentially acts like regularization. In fact, it is an exact form of the regularization we saw in a previous module. This makes my head explode, and I mean in a good way, and hopefully some of this is pretty interesting to you too. Just adding noise to the data points, if you work out the math, gives us a L2 regularized loss. And regularization is there to help with overfitting and with also other problems of machine learning. So we get a lot of a benefit from just applying a little bit of noise and augmenting the data in that way. So some examples. So still sticking to the moons and jitter. Here I'm just loading up all of my libraries because I'm going to need them soon enough. So we're going to do 2D classification. We've already seen support vector machines and kernels. We're going to pretend that this is some small safety critical classifier, and we care about robustness to measurement noise because, again, it's safety critical. We're going to generate a noisy 2 moons data set and split into training and test, train RBF SVM on the original data and on original plus jittered copies of the original. And then we're going to compare training and test, and we're going to look at decision boundaries. And we're going to see whether or not this augmentation will match our invariance assumption. So small little Gaussian perturbations, like normal perturbations to the data inputs, won't change the class. So this is where I do exactly what I just said. We make the moons data set, and we stratify into training and test. Here's our train and evaluation SVM. So nothing too fancy here. It's an RBF kernel SVM with pre-specified hyperparameters, and we're doing fitting and we're storing metrics, and that's basically it. The baseline is to do no augmentation. The kind of empirical model is to do some simple jittering. So the jitter scale will just provide here. Again, this is a hyperparameter that you, in theory, would want to experiment with. But we're going to just add a little bit of normal like a normal noise to the data. So we have the jitter scale we did get from here. This is a scale, if I remember correctly, is like the equivalent of a standard deviation in random number generation.normal. Regardless, like the means should stay the same. Should the expected values of these means should be 0. So we add this little bit of noise to the original training data. We just copy the outputs y, in this case classes, and I mean everything else we go ahead. So we'll do the experiment and compare, and this is the result. We have the 2 settings: the original no augmentation setting and the one with jittered copies. We have doubled the amount of training data from 280 to 560. Initially, the training accuracy was 94.3, and the testing accuracy was 91.7. Both very reasonable. With the jittered copies, we actually get worse training accuracy. So training accuracy goes down, and that might look like a bad thing, but what we actually care about is generalizability in the real world, what happens when we deploy. And performance goes up from 91.7 to 92.5. I think we mentioned also that these small point differences in percentage improvements might seem to be a small thing, and sometimes definitely could be a small thing. We'd want to do some significance testing to just verify that this change is actually meaningful or not. We also talked about scaling, where like a difference in like a fraction of a percent can mean the difference between 0 and tens of hundreds of potential dollars of income. So here are decision boundaries. There's not very much going on here. This is the test data, if I remember correctly. Yeah, so we're just plotting out the test data. So the decision boundaries were determined on training data, but we're showing the data points which are part of the test set. And the difference between 91.7 and 92.5 truly isn't that different, but you can see there's very small, a few examples where a couple of instances might be classified correctly in the jittered copies case. It might be this one over here. So this one purple dot over here seems to be on the yellow side of the boundary in the no augmentation case, and it's on the purple side in the jittered copy case. So I mean, I don't know, but like you can tell, the decision boundary is very slightly different, and a couple of data points will be correctly classified with the latter. So does augmentation reduce overfitting? Like is training like way different than test? Does it make it worse? Actually, I'll leave it to you to figure this out on your own. For decision boundaries, are the decision boundaries really smoother with augmentation? Like when you regularize, decision boundaries are supposed to be smoother. Is that really the case between these two examples or not? Does it extend more confidently into regions where there's injected noise? You can't tell that from looking at the test data, but if you were to redraw this using the augmented data sets here, maybe you'll see some change regarding like movement of these decision boundaries to cover augmented data. Again, all the code is there for you to play with, so try to figure, move around the jitter scale, make it very small, in which case there'll be almost no effect, make it very large to make the data very, very random, so the synthetic data points might drift into regions where label invariance is not something you can assume. Consider model capacity, like a very rigid model might benefit less from augmentation. So change your RBF function to a linear model or something else. Just like everything's there for you to play with and change super easily, like in a moment. The main takeaway here is that even simple Gaussian jitter can act as a data-dependent regularizer. So you can do regularization simply by adding a bit of noise using Gaussian jitter. But you have to be sensible. Your hyperparameters are still something that will matter to your overall performance. And another thing kind of implicit in all of this is that, well, we already started off with very good train and test accuracy. This isn't exactly a situation where we have very imbalanced data. So like the two moons, the purple moon and the yellow moon had more or less the same number of data points. Like I'm leaving it to you. I might even ask you to do it later. Try to downsample, take only 5% of the purple data points and try to train a model and see what happens. See what happens to both training accuracy and testing accuracy, and the story will change. But that's again left to you as an exercise. So that's basically the moral of the story. Another quick example with SMOTE now. So we introduced SMOTE, which is a way of interpolating between existing data points and synthesizing data points in that region. Let's see how synthetic oversampling methods like SMOTE and ADASYN. ADASYN is described in this paper from 2008. It's a somewhat more careful version of SMOTE, which I'm going to kind of skip over the details for now. So let's see how it actually behaves on an actually imbalanced binary classification problem. We're going to have visual intuition through some graphs and some quantitative metrics. So here we're going to construct an imbalanced data set with a positive class, which is going to be very rare. It's going to be a minority class. So positive could be you're positive for a disease, and there's very few people with the disease, so it's going to be rare. And then we're going to compare the baseline, in which we're just going to train on the imbalanced data as it is. And then we're going to use SMOTE, and then we're going to use ADASYN, which is a somewhat more sophisticated kind of SMOTE, where we more or less, instead of just taking samples and then interpolating, like we did with SMOTE. We're going to choose samples that are in hard to classify minority samples, right? So taking examples that are, hard to tell the difference between classes, and then synthesize them carefully so that the decision boundary itself we're not wasting time with data points that are far from the decision boundary. We're focusing on data points that are close to the decision boundary, which is the region we kind of care about most. We're going to use plain test accuracy, and we're also going to use balanced accuracy, which is an average recall across classes, which will be more informative to us than plain accuracy. We talked about recall, precision, F1 scores previously, so consider those as well. And we are essentially using recall here, so we're taking the class imbalance into account. So these methods are not going to guarantee that accuracy will change, get worse, get better. We're just going to do the experiment and see what happens. Again, that's the whole point of this. Like, we're not going to just confirm our pre-existing hunches or hypotheses. We need to test them scientifically without prejudice. And again, also, it might be the case that overall accuracy goes down, but the accuracy in a balanced sense becomes more balanced, right? So I mentioned earlier, if you have one positive example for 99 negative examples, and the classifier just constantly predicts negative, then you kind of expect that the accuracy in general is going to be 99%, but you're going to get 100% recall performance on the negative class and 0% performance on the positive class. We would be happier with a 98% accuracy on the negative class, so a reduction in accuracy, if that also means we're getting a 50% accuracy instead of 0 on the positive minority class. So here's our little example. Here's the code for you to play around with. Anything of note? Here I'm making the classification. So make classification just synthesizes some data. And we've talked about all of the meaning of these arguments already. So I'm using SMOTE. I'm loading it here. So from imblearn, which is a library in Python, you have to add it with pip. There's an oversampling subset, which includes the SMOTE function, which I'm calling here. SMOTE needs a random state for reproducibility, and it needs a certain number of nearest neighbors. This is not a spelling mistake, because this is just technically it is, but it's what the library uses. So I'm not going to fix that, because otherwise this function wouldn't work. But I'm going to use the 5 nearest neighbors in order to compute synthetic examples. And then I'm going to fit on the resampled data and report everything else is just showing you what it looks like. So here's the original imbalance data. I have a majority class, which are these blue circles. I have a minority class, which is more or less a straight line of these orange triangles. There's far fewer of them. But oversampling will, again, just pick some of these and interpolate between them. You can see here's the original leftmost data point. It seems that over here is the next leftmost original data point, and I've synthesized it looks like 4 data points in between them automatically. Okay, so more or less this looks like, again, this is kind of a sanity check. The oversampling I'm doing over here, synthesizing all of these fake orange triangles. This doesn't seem to break anything for me, because that's kind of the pattern that I at least visually observe in the original data. There seems to be a big blue blob and a more or less straight, flat line for the two classes. So visually things kind of make sense. The minority class is very sparsely distributed in the original data, but we filled it in with SMOTE. And we've basically just done some interpolation in feature space, whatever the feature 1 and feature 2 represent. So when classes are imbalanced, plain accuracy will be dominated by the majority class, like I mentioned. So we want to use recall for each class separately. So this is how we do it. We use balanced accuracy. This is going to not be used too often, but it might be a good thing to try to remember anyway. We're going to have k classes. Right now we're doing k equals 2. We're doing binary classification. And recall is defined as it has been before, but we'll compute recall on a class-by-class basis. So we'll have the confusion matrix, and then we'll have the true positives and the false negatives, assuming that class K is positive in each case. So I know initially I said the circles are negative and the triangles are positive. for the point of view of just doing the metrics, I'm going to iterate through all of my features and one by one assume that one is the positive class. So therefore I can compute true positives and false negatives. And this generalizes to k being more than 2. So if I had like 3 or 4 or 5 classes, you'd do the same thing. You'd compute recall for every single class, assuming every class is the true positive for each of these measures. So I have big K classes. I've computed the recall with regards to K for each of them, and then I just take the average of those, and that's the balanced accuracy. In the binary case, this basically is the average of sensitivity, which is the recall of the positive class, and specificity, which is the recall of the negative class. So we kind of brushed over those in the module on metrics, but so far so good. Sensitivity, like high sensitivity and high specificity, are things we want to promote, and we want to promote it in a fair way across positive and negative classes. So far so good. So yeah, if a model completely ignores the minority class, recall will be 0. We don't like that. That's definitely a form of bias, which we'll I think talk about later. So good old-fashioned accuracy might be very high, but balanced accuracy will be extremely low. And again, here we're also weighting each of these classes totally uniformly. So there's no difference between a majority class and a minority class in this balanced computation. So here are results. Again, nothing new is happening here that we haven't seen before. I'm using a scalar to standardize all of the data points. I'm fitting the transform learning on the scale data in all cases. Yeah, and the original data is a baseline. There's no special sampling going on in the, I have SMOTE, where I'm applying the SMOTE oversampling, and then I have a sampler which is doing ADASYN oversampling, which I've imported from the imblearn or imbalance learn Python library. And then I just report the results. So again, I don't quite double the amount of training data between the baseline and the augmented versions, but I have like different numbers of training samples in each cases. Overall test accuracy, like I warned about earlier, goes down when I oversample. So I go from a 91.2% accuracy to like way down to 72.7 and 68.5. It looks like I'm really messing up badly if I'm doing oversampling, because my test accuracy is very bad now. But like that wasn't the point, right? The point was not to totally harass the minority class. Whoop, what happened there? There you go. Like, the point wasn't to totally harass the minority class. And indeed, the test balanced accuracy, which takes the rights of the minority class into account, goes from a horrifyingly low 55.9 up to a 75.96 and a 74.5, given SMOTE and ADASYN respectively. I think I'll mention here just for a moment, normally in my personal experience, like I've encountered tons of these simple classifying experiments using small amounts of data like this. And in my experience anyway, ADASYN normally outperforms SMOTE by a healthy margin. Here it's the other way around. Again, the proof of the pudding is in the eating. You'll never know until you try it. And it's much better as a scientist not to just believe in your assumptions blindly. It's better to do the experiments like we did here. I didn't just assume ADASYN was best and skip SMOTE in favor of ADASYN. So observing the output, you can see how the training points changes for each strategy. You can see how plain test accuracy changes and how balanced accuracy changes. So I just walked over this already, but maybe there might be something else here that you can find that I haven't mentioned. It's always good to take a note of that. So yeah, SMOTE and ADASYN will often improve balance accuracy. Sometimes it could even improve test accuracy in a non-balanced way, but that can be pretty rare. Normally the drops, in my experience, are not as severe as 91 down to 73 or 68.5, but nevertheless, these drops can be tangible, but acceptable in the greater scheme of things. So a few final thoughts. So never augment test labels like for free. The test set should always, be approximate real-world deployment. So obviously you wouldn't mix like augmented test data into training. And usually I advise people to evaluate on non-augmented examples, because there's always a chance that our transformations that we mentioned at the very beginning of this module, big T, are faulty in some way, and the labels are all out of whack. So what we're training on is totally nonsensical. So I like saying, well, we're going to evaluate on real data and not on these transformations. But maybe your transformations are really reliable, in which case, like, I might be persuaded to evaluate on augmented examples. And it's also possible that that's exactly your deployment scenario. Like we talked about before, how the empirical risk of augmented data might be a better representation of the degree to which data can fluctuate in new, ongoing, real-world, new samplings of new data. So maybe that's what your game is. So evaluating performance on augmented test data might be exactly what you want to do. So again, it depends on what you're trying to accomplish. Always monitor training and validation curves. This is not unique to data augmentation, but if augmentation is helping, you should usually see slightly lower training accuracy, or basically not much change in training accuracy, but much higher validation accuracy, especially in the balanced case. And also validation curves should be more stable across epochs and hyperparameters. So you might have seen, we talked about loss curves before, and in textbooks and other classes, you'll see everything going nice and smooth, and it's very cartoonishly smooth. In reality, the curves are going to jump all over the place. If you're using augmentation, you ought to see a little bit more stability across these curves, and also across when you're doing hyperparameter optimization, things should be a bit more stable. Augmentation can be seen as, in a sense, making the machine learning process a bit more stable. But it can also hurt. So if train and validation accuracy both drop, especially if there's no improvement in performance on the minority class, this can be a big red flag. And if the model can't even fit the original training distribution, that this is a sign that you're not doing a good thing. You ought to think about ablations. So I'm going to mention ablations not too formally in this course, but just kind of periodically in situations like this. Ablations are basically a situation where you have a complete pipeline with a lot of different components in the pipeline, and you do an experiment with all those components, and you one by one take components out of the pipeline. And if you can, taking some components out will break the whole pipeline. But you can remove scaling, you can remove other kinds of pre-processing, you can remove augmentation of data points from your pipeline, and you can see what happens. That's a form of ablation. You can see what happens with the module, what happens without the module, and compare them. That's ablation. So what happens when you have no augmentation? What happens when you have one augmentation at a time? What happens when you combine augmentations together in reasonable ways? Just keep on doing as many experiments as you possibly can, given the resources you have available, including your time. The metrics you're using should match the goal. So if all you care about is overall performance, then maybe plain old accuracy will be sufficient. But if robustness to distribution shift is your goal, then evaluating on held out perturbed data that resembles the shift can be good. Again, this is kind of the thing I need to be persuaded on sometimes, but it's sometimes can be reasonable. And also consider worst case or percentile based metrics. So earlier on when we were talking about hospital wait times in a previous module, overall wait times on average seemed kind of fine, and maybe even the overall performance between two hospitals and their 95% confidence interval might overlap a lot. But one hospital might have a small subset of people that have to wait hours and hours. So they're getting the performance on the backs of a poor benighted subgroup of people. Consider what the goals are. There's a Futurama episode, this cartoon called Futurama, where some of the characters have to toil away in some caves. But then the bureaucrat, Hermes of the squad, realizes you can optimize things by just putting all of the work on one little Australian man. So, on average, it's good for people and overall performance goes up. But, the joke there is that, well, this poor Australian has to do the work of everybody now. And it looks good on the surface, but we wouldn't want to be the people who would implement such a scenario. Speaking of which, ethics and risks as usual. Augmentations can sometimes overrepresent some groups or underrepresent others. This is a bit off topic, but you can imagine how the minority class might consist, like if a demographic group is more represented in the minority class than the other, if a certain group, maybe like a subsection of the population demographic group, like race A, is in the minority, but race A has a higher prevalence of a certain disease within that population, but because of the prior, the overall probability of that disease seems to be rare, so it's the minority class. When we're augmenting data, that means we're also augmenting a lot of data relative not just to the disease, but to the population under the disease. So is that safe? Like, is that something we want to be able to do? Sometimes this might hurt things. So like if that's the case and you're oversampling in the minority class in terms of label, now you're suddenly pretending that, this demographic group is 2 or 3 or 4 or 5 or 10 times more populous than it really is. Will this affect your evaluation of bias if you think the two demographic groups or more are evenly balanced because you're dealing with augmentations? And the sky's the limit. Like I'm asking some pretty broad questions here, but you can come up with your own questions. When is augmentation going to break our notion of fairness and equal representation? I should also mention that synthetic examples that are too similar to specific individuals may still leak sensitive information. So imagine like you have some, this is a bit off topic, but you have some data, you apply some privacy preserving methods to like blur out images or remove sensitive information from tables. So now you have privacy preserving, good, like anonymized data. But then you take that data point and you synthesize something similar to that data point. If the model you're using to do that, in the abstract case, maybe you're dealing with a neural network to do augmentations now and not just SMOTE, it'll fill in the gaps. It'll do something like imputation, and it will resynthesize the stuff you previously blurred out, right? And if it has a good model for what faces look like, it might resynthesize a face that looks very similar to the original face, maybe not exactly, but extremely similar, in which case we've re-identified people probabilistically and we've broken privacy. Again, think of other examples where augmentation of this type might hurt privacy. Augmentation in modern machine learning is absolutely all over the place. This is curiosity, so I'm leaving it more or less for you to dig into on your own. I've cited many papers here from the recent past on augmentations in self-supervised learning. So we talked about before, like, just like swapping, like, flipping images, rotating them, adding some noise. This is extraordinarily common in self-supervised learning as a category that we've talked about at the very beginning of this course. Domain randomization, so if you're doing like simulations of worlds and like robotics, for example, you can randomize the world through augmentation. There's techniques similar to augmentation, change textures, change lighting, change object poses, and so on. So augmenting the environment is a little bit different than augmenting individual samples, but it'll produce new data. Like if you're doing like an online synthetic world, changing the world a little bit and sampling from it, we'll give you new samples and give you new models, learn from those new samples. And there's all kinds of policies around learning augmentation. Recent work lets models actually learn for themselves which augmentations should apply. So you can check out this paper for an example of that. And there's still lots of open directions if you're interested in doing research. Are there trade-offs between diversity and label noise? Are there design, how can you learn or design augmentations for structured data? Like not just images where you rotate and add noise, but like graphs, software, molecules, like data where like just small modifications shouldn't matter so much, but graphs, programs, molecules are much more interconnected in terms of what the observed variables are. So, you can't just make augmentations willy-nilly. So how do you go about augmenting data in these much more complicated tasks, like, synthesizing new DNA strands, for example? Here are our quick checks, and all of the math, there's not much math here, but it looks fine. So go ahead and do that, please. So in summary, data augmentations create synthetic or fake training examples that ideally preserve labels, or if they modify the labels, they do so in equivariant ways, in predictable ways. This will encode inductive bias, so like the model should be invariant or equivariant to these changes. An important, interesting thing with the little mind being blown at the bottom is that augmentation of certain kinds will augment the empirical risk and can actually act like an implicit regularization. There's a direct correspondence between doing L2 regularization and the kind of augmentation we're doing with just doing a bit of jitter with Gaussian noise from today's module. Practically, like, we're doing this to improve robustness, to improve generalization. We're also doing it, not mentioned right here, but we're doing it in order to help balance the distribution between majority and minority classes, so that we're not unfairly disadvantaging the minority class. This is similar to generalization and robustness, but it's slightly different. As always, we want to evaluate carefully. You want to evaluate with crossfold validation, clean validation. Make sure there's no test in knowledge getting into your training. And also know that modern machine learning heavily uses augmentation. So, every topic we're talking about now has sort of echoes in modern machine learning, and a lot of them are being used directly, and in particular, augmentation is absolutely all over the place in modern machine learning. As you go ahead and work on labs and assignments, you should treat augmentation as like a design choice, just like everything else. It's a little module in your pipeline. It's not like, yeah, we've done augmentation, check, we've improved the pipeline. Simply adding augmentation does not mean you've improved the pipeline. It's not a checkbox you can check. You have to be careful. Here's the references. As always, it's a pleasure. See you next time.